Introduction. The sense of touch is crucial for safely interacting with objects and for the perception and self-awareness of humans. It is also essential for the development of intelligent robotic systems that can autonomously explore their surroundings. Researchers have been exploring various sensors to create an artificial sense of touch, but current technology is still far from matching the tactile sensing capabilities of humans. Therefore, there is a need for further advancements in this field to enable robots to safely interact in dynamic, unstructured environments. The tactile sensation and perception in human skin and the evolution of artificial tactile skin in robots. Skin is the major component of human PNS, which has inspired robotic tactile skin research over the years. The tactile sensing technologies have advanced from single touch sensor to large area skin, middle covering the whole body of a robot, right? This poses challenges in data handling and energy consumption. The images, from bottom to top, in the timeline middle, are adapted from with permissions. Distributing computing in tactile skin can further boost the interaction capabilities of robots. The block diagram below shows the key steps to attain the same and outlines the structure of this paper. Developing an artificial sense of touch for robots is crucial for safe interaction in uncertain environments. However, current tactile sensors lack reliable data processing capabilities. While analytical and data-driven approaches have been used, they have limitations. To improve tactile sensing, hardware needs to be physically distributed and use neural-like processing to learn multiple levels of features. With increasing numbers of sensors generating large amounts of data, efficient and low-power electronic hardware is needed. This review presents a comprehensive discussion on the computing element in tactile sensing and how it can be implemented using various building blocks and algorithms. The advances in flexible and printed electronics technologies could lead to the development of large-area computational e-skin, opening up new application avenues in diverse areas. The neural pathways for tactile data processing in human skin and their simple implementation schemes using basic devices and circuits. A neural pathway for tactile data processing. The sensing data are collected in the sensory neuron first order, passed to the cuneic neuron second order, and finally sent to the higher levels of the nervous system. The key components, mechanoreceptors, neurons, and synapses of human body involved in tactile sensing and data encoding are shown with the illustrations of their simple implementations through electronic devices and circuits. The SA and FA mechanoreceptors are usually mimicked by a stack of capacitive and piezoelectric sensors. The RC circuit 2. Emulates the action potential of the spiking neuron. Memristors or similar devices 3. Can be used for the implementation of various synaptic functions such as time and rate-based learning rules. The rate-based learning rule refers to BCM, Bienenstock, Cooper, and Monroe learning rule. B. Possible tactile data processing at the first-order neuron, reprinted with permission from. C. Possible tactile data processing at the second-order neuron. The skin has a large number of mechanoreceptors that respond to stimuli of various frequencies, and each subtype of receptors has a different receptive field size. The understanding of tactile perception is less developed, but some level of computing takes place in the skin itself. Achieving edge computing at the skin level could greatly lower the data transmission burden, and the firing pattern of several neurons at the same time could trigger the firing of the next level neuron. This lays the foundation for tactile signal computing using the STDP learning rule, but other possible learning rules can also be implemented in the e-skin. Artificial synapse. To replicate the synaptic functionalities of neural networks in hardware for the proposed e-skin, resistive random access memory RRAM, phase change memory PCM, magnetic random access memory MRAM, and ferroelectric random access memory FERM, have been explored as alternatives to CMOS devices. These memristive devices on flexible substrates exploit changes in physical properties of the materials in response to external electrical stimuli to mimic the synaptic behavior. Memristive crossbar arrays are a concise route for synapse implementation. For artificial neural networks, synapses operate using single pulse signals with multilevel weight tuning. For spiking neural networks, SNN, synapses operate using a pair of pulses after various biological learning rules, such as STDP. Future development of large-scale synapses for e-skin should be carried out on soft substrates. 3. Hardware implementation of artificial synapse. Various 2 and 3 terminal devices as artificial synapses including RRAM, PCM, floating gate transistor, and FEFET. The schemas of the RRAM, PCM, and floating gate transistor are redrawn based on B. Matrix vector multiplication in crossbar arrays with both active and passive memristive devices. Potentiation and depression characteristics of analog memristive devices. C. Synaptic behavior as excitatory and inhibitory with long and short-term plasticity. D. Hardware implementation of some memristor-based artificial synapse in I, and with integration of memristor crossbars and CMOS chips on wire-bonded pin grid array package. Inset shows the testing setup and 2. SNN, reprint from with permission, using PCB with passive memristor switching matrix. Inset shows the scanning electron image of memristor crossbar. E. Localized neural pathway for robots. I. Distributed sensorimeter merging that leads to the learning of the maze exploration of the robot, adapted from with permission. 2. Distributed sensorimeter correlation that leads to the acquisition of the pain reflex. Toward computational E-skin implementation, flexible PCB and chip thinning technology. Flexible printed circuit boards PCBs have been used to integrate sensors and electronic components for E-skin on soft substrates. Neuromorphic chips offer a platform for in-hardware computing capability using deep neural networks, enabling various computing tasks required by robots. However, achieving human-level tactile sensation and perception relies on the intricate interplay between the softness of the skin and spiking response of neurons, using a shallow network of 2 layers. For the technological advances to implement large-area computational E-skin on flexible substrates. A. The energy autonomous E-skin with graphene-based transparent touch sensing layer on robotic hand and on flexible solar cells. The backside of the solar cell shows rigid off-the-shelf chips. Images adapted from B. The neuromorphic chip, True North, with 1 million spiking neurons implemented using digital electronics. CUDC technology could be used to obtain a flexible version of neuromorphic chips and hence the computational E-skin with greater flexibility. D. The roll-to-roll printing of various computing building blocks for the future E-skin. The feasibility of such E-skin is evident from the examples of printed electronic layers and devices, ion 2 transfer printed C nanoribbons and transistor made from them. 3. Contact printed nanowire-based devices. Integrating soft and rigid materials in E-skin limits bendability and increases the chances of failure. Thinning the chips using ultra-thin chip technology and bonding them onto flexible PCBs could offer greater flexibility. However, conventional chip bonding methods may introduce cracks in the chips, which could be resolved by bonding by printing. Reliable interconnects could be addressed by using mechanically flexible conductive materials such as liquid metals. Despite challenges and limitations, using UTCs with flexible PCB is a possible solution for realizing computational E-skin. Conclusion: the development of a sensitive tactile sensory system is critical for the next generation of intelligent and autonomous robots to safely interact in unstructured and uncertain environments. Current E-skin research focuses on tactile sensation and integration on flexible substrates. This review article focuses on the computational aspect of E-skin and its integration with the peripheral nervous system (PNS) to efficiently process tactile data. By mimicking the biological neural pathway of touch, E-skin could provide preliminary perception capability and decrease cognitive load on central control unit. Advances in printed and flexible electronics could also benefit E-skin development. Overall, this article aims to inspire future advancements in E-skin research and improve the responsiveness of robots to human-like levels.